All right, so next up, we're going to talk about kind of two sort of disjointed topics. First, we're going to talk about domain and range, and then we're going to talk about simplifying radicals using rational exponents instead of using the radical form. Okay, so first off, domain and range. So, quick review: domain, remember, is the set of all possible x values. Okay, and then range is the set of all possible y values. Possible y values. There we go. Okay, so domain is a set of all the possible x values. Range is a set of all the possible y values. Okay, so we're looking at a function and we're thinking, okay, what are all the possible things that this could be? Okay, so we have a bunch of different types of graphs here, and we're just going to take a look at these and think about what the domain and range are going to be. So the first thing that I always do when I look at these is I sort of make like a little baby sketch for myself. So I have an idea of generally what this thing looks like. So this guy right here, I know is a line. Okay, and I mean, I could be a little bit more specific about the fact that it's a line. Like I know the y-intercept's -2 and the slope is 3, so it's sort of like steepish. It's going to be something like that, right? So this is the general idea of what this graph looks like, and that's going to help me figure out my domain and range. Okay, so over here, I'm going to do domain and range. Okay, and we're going to write this in a particular notation. So for my domain here, the domain is all the possible x values. So I'm looking at this graph and I'm thinking, is there ever going to be a spot where this graph won't get to on the x-axis? Right? And the answer is no. This graph is always going to keep going farther and farther sideways. It will eventually get to every number on the x-axis, right? You're eventually going to go sideways enough to get to any point whatsoever. So my domain for this one is all real numbers, which we use this lovely little symbol here. It's like a capital R with an extra line through it. So all real numbers work for the domain for this function. The range is the y values, and similarly, this graph is always going to keep getting higher and lower. So my range is also all real numbers. Okay, so that one was pretty easy. Let's take a look at this next one. So this guy, this one's a quadratic, all right, and I know, let's see, it's been shifted down 3. So it's a quadratic that looks something like this. Great. Okay, so from here, what I'm going to do is I'm going to figure out what my domain and range are. All right, and remember this guy down here is at -3. So my domain for this guy is I'm asking about the x values. Is there ever an x value that isn't going to work for this? Is there any a value every time wow? Is there ever a value of x that this graph won't reach? And the answer is that the graph is going to reach all of them, right? This will continually get wider, slowly, but it'll eventually hit every possible x value. So your domain, again, all real numbers. But the range is different because you can see from this graph, it's going to keep getting higher, but it never goes below -3. So here's how we're going to write the range for this one. We're going to start with a brace. Those are those like squiggly parentheses. Okay, and you're going to write y and then a colon. And the way that you pronounce that is you would say such that. Okay, so it's y such that. And in this case, the y values are always greater than or equal to -3. Okay, so my domain, or I'm sorry, my range is y such that y is greater than or equal to -3. Okay, so it's a slightly different notation you may not be used to, but we're gonna get used to it. Okay, this guy right here, again, I'm thinking about what this looks like. This is an absolute value graph, so I know it's a V shape, and it's been flipped, and it's been shifted over some, right? So it's been shifted over to the positive side 3 spaces. So this graph is going to go something like this, right? Okay, great. So again, domain. For my domain for this, I'm going to eventually hit every x value. So once again, the domain is all real numbers. It's not always all real numbers, but a lot of times it will be when you're talking about functions. All right, and then for my range, well, my range is that the y's are always 0 and under, right? So y is always less than or equal to 0. So again, brace, y colon, so y such that, and in this case, y is always less than or equal to 0. There we go. All right, next guy. So this one is a square root function, and it's been shifted up 2, right? So my graph is going to look something like this. All right, so my domain, oh, finally, one that's not all real numbers. So the domain for this one, right, I'm only ever hitting x values that are 0 and larger, right? I'm never getting negative x values. So my domain is going to be same thing as the last one, brace x such that, and in this case, x is greater than or equal to 0. There we go. And then for my range, brace, and it's going to be y such that, in this case, right, we had a vertical shift of 2, right? So my y values are always greater than 2. So greater than or equal to. So y is always greater than or equal to 2. So you kind of see how just having the picture can really be helpful sometimes. Like some people will just do these and sort of just memorize like, oh, I know what the shape of this graph is and therefore I know this about it. And that's useful for some things, like the line. Anytime I have a line, I just kind of automatically know it's going to be all real numbers for both, with the only exception being if it's a horizontal or a vertical line. Okay, I know that if it's a quadratic, it's always all real numbers for the domain. So you could memorize things like that, but if you just give yourself a little sketch of the graph, I think a lot of times that's just as easy. Okay, so this guy, square root graph, and it's been shifted to the right 3, right? So it's something like this, where here's 3. Okay, so for my domain, oops, that's not a D. Okay, so my domain, right? All of my x values are 3 and larger. So I'm going to write x such that x is greater than or equal to 3. Okay, and then for my range, y such that y is greater than or equal to 0, because it's always above the x-axis. All right, and then this last one. So this one's going to have a little bit going on with it, but that's all right. We can handle this. Okay, so thinking about the sketch of what this graph is going to be. I know it's been shifted up 2, right? And it's been shifted to the right 3. So up 2, right 3. There's my starting point. And normally my graph, my square root graph would go this way, but I have a vertical flip, so it's actually going to go that way. I sort of ran out of room there, but you can sort of see what it looks like. Okay, and this was at 3, and this was at 2. Okay, so my domain, right? All of my x values are 3 and larger. So it's x such that x is greater than or equal to 3. And then my range, right? Well, it's 2 and under, right? So my range is y such that y is less than or equal to 2. And there we go. Okay, so again, strongly recommend you just give yourself a quick little sketch. These aren't very detailed sketches, right? I mean, for the most part, I don't even have numbers or anything on there. I just have a couple of numbers when there's like a cutoff point in the graph, because that helps me out. But like, they're pretty simple sketches. So give yourself a quick little sketch, and that's going to help you as you're setting up what your domain and range are. All right, so that is kind of topic number 1. So topic number 2 is we're going to talk about simplifying using rational exponents, okay? So what you want to do is you want to use this when your indexes don't match. So if the indexes don't match, okay, and your radicands can be written as powers of the same base, okay? So the radicands can be written as powers of the same base. I apparently did not give myself enough room to fill in that blank. So when the index numbers don't match, but the radicands can be written as powers of the same base. Okay, so let's take a look at this guy. Clearly our index numbers don't match. That one's a 4, that one's a 2. Okay, but 8 and 32 are both powers of 2. So what I can do here is I can rewrite this, right? I'm going to start by just rewriting the radicands as powers of the same number. So I'm going to rewrite this as 2 to the 3rd. And then I'm going to rewrite this one as 2 to the 5th. Okay, so step 1 here All right. The first thing that I did was I rewrote the Radicands. So rewrite the Radicands. Okay, and now what I'm going to do is I'm going to convert these into exponent form. So remember, it's power over root. So I'm going to write this as 2 to the power over root. So power over root. So 3 over 4. And then this one, 2 to the power over root. So power over root. Remember, that's a little invisible too. So that's 2 to the 5 halves. Okay, so step 1 was rewrite the Radicands. Step 2 is we are converting, and we're using power over root to do that. Okay, and now I can use my exponent rules, right? My exponent rules say that if you have two numbers with the same base and you're multiplying them together, that you add your exponents, right? As a quick example, right, if I had like 3 to the 5th power times 3 to the 2nd power, that's the same as 3 to the 7th power, right? Multiply 3 5s by 2 more 5s, that's 7 5s altogether. So our shortcut is that you add your exponents. So I'm going to do the same thing here. I'm going to add 3/4 and 5 halves. So a little bit of scratch work, 3/4 plus 5 halves. I need common denominators, so I'll multiply this guy by 2 top and bottom. So that's 10/4. So that's going to work out to 13/4, right? Okay, so we added our exponents. So now it's 2 to the 13/4. Okay, and again here, from here to here, I just use my exponent rules. All right, and then you just want to make sure that since the original problem was in radical form, we want our final answer to be in radical form. So I'm going to convert this back, right? So power over root, so 2 to the 13th with the 4th root. Okay, and then from there, you just want to make sure it's totally simplified, right? I can take sets of 4 out of 13 twos, right? I can take, let's see, 4, 8, 12, 3 sets of 4. So I'm going to have 2 to the 3rd power on the outside, right? And then it's the 4th root. I'm just going to have a 2 left over. Okay. If you had trouble following that, right, we had 13 twos, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So I said, okay, well, here's a group of 4, here's a group of 4, here's a group of 4 with 1 left over. So 3 sets of 2 on the outside, 1 left over on the inside. And of course, we can simplify that to 8 times the 4th root of 2. And there's my final answer. Okay, so that right there was our convert back. And then we just simplified a little bit. Okay, so it's a kind of it's a handy little trick that you can use. Again, tends to be one of the more overlooked things when people get to like tests and quizzes on this material. So just make sure you kind of keep this in the back of your head. So this guy right here, again, indexes don't match, but 9 and 81 can be written as powers of the same thing. So I'm going to start by rewriting this as 3 squared and 3 to the 4th power. Okay, then I'm going to convert it into exponent form. So power over root. So 2 over 3, power over root, 4 over 5. Okay, and then from there, I can add those exponents together. So 2/3 plus 4/5, right? I need common denominators. So I'm going to multiply this guy by 5 top and bottom, and this guy by 3 top and bottom. So that's going to give me 10 over 15 and 12 over 15. So that's going to add to 22 over 15. So this is 3 to the 22 over 15. Convert that. Power over root. Okay, and then from there, I can take a set of 15 threes out of that. So I'll have 1 3 on the outside. And then when I take those out, I'm going to be left with 7 threes left over. So 3 to the 7th on the inside. You can write this out, like actually figure out what 3 to the 7th is if you want to, but it is a rather large number. So it's okay when you have some of the higher powers if you just leave them that way. If it's something small, like 2 to the third, I do expect you to multiply it out. But like 3 to the seventh, that's a really big number. So you don't have to worry about writing that whole thing out. It's okay if you just leave it that way. Okay, so that is how you're going to use rational exponents to help you simplify, and how you're going to figure out domain and range depending on different functions that you're given.